So now let's go back and look at an example of the independent samples t-test. So remember our research question here. Do employees under transformational leaders have higher performance ratings compared to employees under transactional leaders? Our IV is the management strategy. We have two groups, a group that had a transactional leader and a group that had a transformational leader. And then we're looking to see if their performance ratings are different across these two groups. And we do that by comparing the means. And if you remember, our group 1 mean was 6.12, our group 2 mean was 8.15. And so our question is, are those numbers, 6.12 and 8.15, are they so different from each other that we can declare that there is a statistically significant difference between these two numbers, right? Remember, if they were both equal, we'd say, well, there's no difference. On the other hand, if it was 6.12 and 6.13, we'd say, I don't know if that's a big enough difference. Like that could just be error. What if it was 6.14? What if it was 6.15? What if it was 9? What if it was 7? How big of a difference matters? The question is, the numerator is of our test statistic is about how big the difference is. And then we say it's statistically significant when we say it's more than we would expect, right? Remember that standard error is there on the bottom. Where do we get our standard error? From the standard deviation in the sample size, which we can get from our sample, right? So we take these 6 numbers and we can put them into our t-statistic and come up with an answer about, is 6.12 and 8.15, are they so different from each other that we can say there is a systemic difference here? Now remember, this is a directional theoretical hypothesis that we're saying that transformational leaders should have a higher mean than transactional leaders. But we're going to test it using a two-tailed test because it is more conservative. So again, we just plug and chug into our equation. We have our equation for t is the difference between the two sample means divided by the pooled standard deviation. So 6.12 minus 8.15, that's the difference between the two means, divided by the pooled standard deviation, which comes out to 0.44 if you do the math. So 2.03 divided by 0.44. Our t-statistic in this case is negative 4.65. Look, the positive versus negative is just about because I did 6.12 minus 8.15. If I'd done it 8.15 minus 6.12, I'd have a positive, right? It's just about the difference between those means. So you do have to look at what the direction is, and that's what that positive versus negative is really telling you here. So the difference between 6.12 and 8.15 is 2.03. Divide that by a standard error, the pooled standard error 0.44, and what I get is a t of 4.65. And the question is, how big is that t, right? If it was 0, we would say not statistically significant. If it was a gazillion, we would say very statistically significant, or we wouldn't say very, we would say it is statistically significant. 4.65, I don't know. How many degrees of freedom do I have? Well, I have 50, right? Because I have N1 plus N2 is 26 plus 26. I have 52 total people in my sample minus 2, right? Because degrees of freedom is the total sample, all the both samples combined, minus 2. And then also I get 50 degrees of freedom. And if we go take a look at that, we say, all right, 4.65 on 50 degrees of freedom. What do I know? Well, the critical values, and you can Google this or you can look it up in a chart or whatever, the criticals of values of t for 50 degrees of freedom in a one-tailed test would be 1.66, and in a two-tailed test, it's 2.01. Right, so you can see again here, it's a more stringent test to have the two-tailed test, which is why I use that one. Now in this case, I'm much higher than either one of those, so it kind of doesn't matter. I can calculate that p directly for 4.65 on 50 degrees of freedom, and I get p, the probability of getting 4.65 if there's actually no difference between these populations, right? That's what that p means. If there were no difference in these two populations, the odds or the chances, the probability of me getting 4.65 for my t-statistic is 0.0025% of the time I would get that. So very, very small, right? And don't forget, we would typically say, if our p is less than 0.001, we just say less than 0.001. If it's greater than 0.001, we say what the actual p value is. But the point here is that there's a vanishingly small chance, almost no chance, that I could have gotten a t that large if there was in fact no difference between the means of these populations. So This is how we write our conclusion now. In our two groups, employees with transformational leaders had performance ratings that were statistically significantly higher than employees with transactional leaders. And then I throw in the statistics to back this up, right? So my mean for my transactional was 6.12. My mean for my transformational, 8.15. Alternatively, a way to write this, you might put the difference between means was 2.03, right? T with 50 degrees of freedom was 4.65, P less than 0.001. So in our two groups, employees with transformational leaders had performance ratings that were statistically significantly higher than employees with transactional leaders. The mean of transactional was 6.12, the mean of transformational was 8.15. A T on 50 degrees of freedom was 4.65, P less than 0.001. That is the statistical significant or statistical sentence by which I communicate the results of my study.